It's our honor to have Professor John, Wisdom, to have Professor John to be with us today. Let's welcome him. Okay, everyone, please open to this page. So are you all ready? Okay, everyone, please see the top figures. So the center is low pressure region, right? So the air at the surface will move toward from the surrounding regions. Okay, so the air at the surface move toward the low pressure area from the surrounding regions. Alright? So as the air converges, you can force raise upwards. And this rising motion can help form clouds and unstable weather. Okay, so keep this one in mind. So the low pressures centers and the surface air moves in. Then rise, right? So let's write this one down. So in the opposite, in this bottom figure, the center is high pressure regions. So the air moves downwards from above into the high pressure area. Okay? So after thinking, the air spreads upwards at the surface. So this usually surprises the cloud formations and often associated with more stable weather. So in opposite, high pressure, for a high pressure center, the air is going to stink. The air stinks, and then surface air moves out. Understand? So you okay? So may I move on to the next page? Okay, next page. So this slide is going to introduce atmospheric stability. So first I want to define Okay, so this slide is going to talk about the atmospheric stability. So the first one I want to define. So this is the definitions. I want to define what atmospheric stability is. So this means the tendency of atmospheres to resist vertical motion, the vertical lift. And also, this usually relate to something called lapse rate. So what's lapse rate? So lapse rate is the rate at which air temperature changes with time. So air temperature changes with height. Okay? So the stability is usually related to this so-called lapse rate. So this is the rate at which air temperatures changes with height. Okay, and this slide focuses on something called stable airs. Okay, meaning the neutral stability. So in this case, atmospheric temperature profile matches the adiabatic lapse rate. Okay, so as you can see, in these figures, so the ambient lapse rates shown in this figure is minus 1 degree Celsius per 100 meters. Okay? And this value matches the dry adiabatic lapse rate. Okay? So you can see that. So upwards 100 meters, the temperatures becomes 20.15 from 21.15. And downwards 100 meters, okay, the temperature becomes 22.15. Okay, because the temperature changes every 100 meters. Okay, so the delta T over delta Z is negative, is minus 1 degree Celsius per 100 meters. Okay, so let me summarize this slides. So this slide is about the stability. Okay, so stability is about the tendency of air resist vertical motion, and it depends on something called lapse rates, which means the changes of temperature with height. Okay, so in neutral stability, the environmental lapse rate equals the adiabatic lapse rate. However, as the height changes upwards or downwards, the temperature will change. Okay, and because this is a minus value, right? So if you go upwards 100 meters, the temperature becomes 20.15. And if you move downwards, the temperature becomes 22.15. So next slides, I'm going to talk about the unstable. I would like to differentiate the difference between unstable air and stable air. Okay, so in unstable airs, the thermal structures enhance turbulence. Okay, let's highlight this. Let's underline this. The turbulence. Okay, and this happen to something called super adiabatic. Okay, the super adiabatic means the air temperature decreases with high, faster. It means the air temperature decreases with high, faster than the adiabatic lattice rate. Everyone knows that? So we call this super adiabatic. Okay? So unstable air atmosphere enhance turbulence. And the lattice rate is super adiabatic, which means the temperature decrease was high, faster than the adiabatic lattice rate. So in opposite to stable air, so in stable atmospheres, the thermal structure inhibits. So one is enhanced. The other one is inhibits. So the thermal structures inhibits turbulence. Okay? And this occurs when environmental lattice rate is something called sub. So one is super, the other one is sub-adiabatic. Okay, so in opposite, that means the air temperature decreases with high, slower. And write this one down. Slower than the adiabatic lattice rate. Okay? So before I move on to the next slides, okay, I want to review this. To summarize this, listen up. In unstable air, the temperature decreases rapidly with high. Okay, we call this super adiabatic. Okay, because it enhances the turbulence. Okay, on the other hand, in stable air, the temperature decreases slower with height. And we call this sub-adiabatic. Okay? So, unstable. Okay. Everyone okay with that? Okay. So, next slides, I would like to talk about the formation of sea breeze during the daytimes and night times. Okay, so during the daytimes, okay, because the temperatures, okay, the temperature, the land is warmer, right? So the land heats up faster than sea. Okay, the sea is cooler. Okay, so the land is warmer, the sea is cooler. Okay, that means the land heats up faster. Than the sea. Okay, as a result, the warm air raises up, right? The air above the land becomes warmer. Okay, what does this mean? The air becomes warmer, that means the density decrease. Less dense, right? The density decrease and raise. Okay, and the sea remains relatively cooler. So the air above, okay, the air above the sea is denser. Okay, so the density increase, so it's thick. Okay, and then this cool air gonna move from the sea to the land. So we call this sea breeze. We call it sea breeze. You understand? And during the long times, you're gonna generate something called land breeze. Okay, just totally, everything just totally opposite, right? So the land is cooler at nighttime, and the sea is warmer. So at night, the land cools down faster. Okay, the land cools down, so it's warm faster. Okay. Heated faster, and this becomes cools down. So once heats up faster, and this is cool down faster. Okay, the land cools down faster than the sea. Okay, so and the sea stays relatively warmer than the land. So therefore, the air above the sea becomes warmer and raise. So the air above the lands becomes cooler. Okay, and it's dense. The density increase. The density increase becomes dense. So it flows from the land to the sea. Okay, so let me summarize here. So during the daytime, the land warmer and the sea cooler. So the wind blows from sea to land. Because the density of air above the sea becomes becomes denser. Okay, so it's thick. So the winds blow from the sea to land. And we call this sea breeze. And in opposite, during the night time, the land is cooler and the sea will be warmer. So this wind is above the sea, right? So in opposite, the wind above the land blows from land to sea. And we call this land breeze. We call this land breeze. Okay? Okay. Okay, let's see this figure from our textbook, the figure 9-21. So this slide explains the effects of the lake breeze, okay, same as the sea breeze, right? The land breeze on the balloons, okay? Balloon is just like a smoke. The balloon dispersions from the smoke stack near the shorelines. Okay, so if we have if there is a chemical plants near the shorelines, okay, will the lake breeze affect the balloons? Okay, of course. Okay, of course. So I want to define two terms. Okay, one is called fanning. The other one is called fumigations. The fanning and fumigations. Okay, so the fanning balloon means that. So this balloon is close to the lake, right? So the air above the lake, okay, is cooler. Okay, as we just mentioned, right? The air above the lake is cooler. So we have a cooler air above the lakes. Okay, which usually is stable. Okay, so this is stable. And the vertical mixing is weak. So that means the balloons, the smoke, sprays mainly horizontally. Okay, mainly horizontally. And we call this fanning balloon. The fanning balloons. Okay, so this is why near the stack, the smoke, the balloons looks like sting and flakes. Okay, however, in the inlands, so this is inlands. Okay, as the air moves inlands, as I just showed you in this, right? The land is warmer. So as air moves inland, the land surface becomes warmer than the lake surface, right? And also the lower atmosphere over the land becomes unstable. So we have vertical mixings. Okay, the vertical mixings. So the vertical mixing increase. Okay, the vertical mixing increase. So after like several kilometers, the balloon mixed downwards to the grounds. So we call this kinds of balloon fumigations. Okay? So let me summarize this for you. So near the lake, stable air, not much vertical mixings, and it produced something called fanning balloons, which is thin and flat. However, far from the lake, moving to the inland, the air becomes unstable. And the vertical mixing increase. Okay, you're going to generate something called fumigations. Balloons. All right? Okay, please write down. Okay. So if you don't understand, okay, as I mentioned to you many, you might read a passage. Okay, you might read a passage. Okay, so this figure is from passage. All right? Everyone okay? May I move on? Okay, so this course is not environmental science. For environmental science, we don't have too much mathematics. But this course is environmental engineering. So we have some mathematics. For example, like this slide. Okay, this slide explains the effective stack heights. Okay, so based on the formula, we can calculate the actual heights at which pollutants are released into the atmosphere. Okay, after accounting for the balloons race. Okay, so first off, so the capital H here, this is effective. So the capital H is effective stack height. And the small letter H here, this is the real, okay, the physical stack height. Okay, like this one. Student, take a look. So this is small letter H. Okay? So the capital H is the effective. The capital H is the effective stack heights. Okay, the small letter H is physical. Okay, the actual, the physical stack height. And delta H is the balloon race. Okay, so if we use the figure 9-21, so this is delta H. Okay, so this is capital H. Doing okay? So the actual, the physical stack height is small h. The balloon, the height of balloon is delta H. So add these two up, the capital H is something called effective stack height. Okay, so this formula 9-27, how you to calculate delta H? Okay, theoretically. So the Vs is the stack velocity. And D is diameter, stack diameter. So U is another velocity, another speed. However, this is wind speed. You also need to take the wind speed into account. Okay? So one is stack velocity, stack speed. The other one is wind speed. Okay, wind speed. So P is pressures. Okay, P is pressures. The unit is kilopascal. Okay, we have two temperatures here. One is TS. The other one is TA. So the TS stands for the stack gas temperature. Okay, you need to use Kelvin for its unit. Okay, you need to use Kelvin for its unit. And the TA stands for air temperature. The TA stands for air temperature. Okay, so by using this formula, 9-2027, you can find out delta H. Okay, then you end up with the physical state cost. Then you can find out something called effective state cost. All right? Okay. So next, I would like to show you the Bruin standard deviations. Okay, the Bruin standard deviations. So first one is SY. So SY is the S stands for standard deviation, right? And SY is the standard deviation of balloon's concentration in horizontal directions. Okay, the Y stands for horizontal directions. So the XZ, of course, stands for vertical. So SZ is the standard deviation of balloons concentrations in the vertical directions. Okay? And these two standard deviations, these two values, okay, tells us how wide and how tall the balloon becomes as he moves downwind. Okay, so this is empirical formula. Okay, this is empiricals. Okay, derived by this guy, okay, D.O. Martins in 1976. Okay, these two are empiricals, which is based on the experimental results and theories. Okay, so the value is this. Okay, so after that, after calculations, okay, the value can be classified into. So this is stability class from A to F. So the A means very unstable. Let's write this one down. Okay. The capital A, not small letter A. The capital A means very unstable. Okay, very unstable. And B and C means slightly unstable. So B and C means slightly unstable. And D means neutral. And E and F means stable. So I would like to ask Okay. Good. Tom?
Yeah.
Okay. Why we, in this table, why we have this one? Okay, x smaller and equal 1 kilometer, and another part x larger than 1 kilometer. What do you think? How can we have these two? We're gonna separate. How can we gonna separate this table into two? What do you think?
I guess the values are different from what x is, so we have to separate them.
Yeah.
Like the values for C, D, and F.
From this figure, what do you think?
That it's different from fumigation and fanning.
And it's related to distance, right?
Yeah.
Yeah, I think the distance matter, right? Student, the distance matters for the fanning and fumigations, right? So in this tables, that's the reason this table 9-14 from textbook separates. Okay, we'll separate into like x smaller and equal 1 kilometer, and the other side x larger than 1 kilometer. This is because the balloon spray behavior changes with distance. The distance matters. Okay? The distance matters. So the different constant, that's the reason the different constant are used for short distance and long downwind distances. Okay, one more thing before we move on to the first questions, that first part of this questions. Okay, this slide, also from the textbook. Okay, so this slide help us to calculate the ground level concentration, which means the pollutants. Okay, the pollutant concentration at the ground surface. Okay, pollutant concentration at the ground surface after the balloon is emitted from the stack. Okay, so equation shown here. So this X means the downwind concentration, which means you can add this up, which means the pollutants concentration. Which means the pollutant concentration at ground level. And the capital E is emission rate of pollutant. Okay, the downwind, the textbook say downwind, but you can regardless as pollutant. Okay, as a pollutant concentration at the ground level. Okay, that may make this easy to understand. And capital E is emission rate of pollutants. Okay, and we are in there as Y and Z, right? SY is horizontal balloon spray parameters, and XZ is a vertical balloon spray parameter. You need to calculate. Okay, use those parameters. Okay, use those values and find out. And the white So the u is the wind speed. S, Y, Z is distance. Okay, but I want to mention y specifically. The y equals the crosswind distance from balloon center line. Okay, S, Y, Z, and H, all of them means distance, but I want to point out why. Because y is the crosswind distance from the balloon center line. Okay, and H is what we just learned, right? So H is something called effective. It's something called effective stack point. Okay, let's do this question before we take a short break. Okay, so let's see this example from test script. Okay, so let me give you a stability class D. Okay, it has been estimated that the emission of carbon dioxide from coal-fired power plants is 1,656.2 gallon per second. At 3 kilometer downwinds on an overcast summer afternoon. So what is the single line concentrations of carbon dioxide? So if the wind speed is 4.5 meter per second, okay, the center line implies y equals 0. So what do we have here? First we have, so what is this value? So this value, student, this value is E. This value is emission rate. So we have E here. Okay? And the 3 here, this is downwind distance. This is downwind distance. So this is X. This is downwind distance. Do we have a wind speed? Yes. Here's the wind speed, 4.5. So this is U. Okay? So for the calculation questions in environmental engineering, if you know how to apply formula, okay, you are totally fine with that. I will not ask you to derive that. Okay, it's unlike unit operations. And do you have a diameters for the stack? Yes. So so this is D. This is D. So this is the stack diameters. And this is small letter h. So this is physical height of stack. Okay? And instead velocity. So this is Vx. Okay, we also have temperatures. But I just mentioned that you need to convert temperature from degrees Celsius into Kelvin. So this is temperature, but you need to convert it to 588 Kelvin. Okay, but write this one down. This is stack temperature, not air. So we have air temperature here. The air temperature is 25 degrees Celsius, which means 298 Kelvin. Okay, and also we have pressures. Okay, we have pressure here. And we have D, and also we have Y equals 0. So plugging all the data, okay, do it before we end today's, not today's class, and end the class this section. Okay, I'm gonna give you 3 minutes. Okay, so for the questions I'm going to ask, okay, I will not ask you, I will not ask you to derive the equation, okay? I will just ask you how to apply equation for the questions. 不会叫你推导，只会叫你应用。Okay, so you need to know how to use it. Understand? So we have everything. Okay, we have everything here. Okay. So, student. Okay, let's do it. So actuaries, okay, student. So first off, you need to find out delta H. Okay, first off, you need to find out delta H. Use the formula here. Okay, you need to find out delta H. Okay, so the delta H is 8.0. Okay, and the actual, the physical height of the stand is 120, right? So add up 8.0. So 128, this is something called effective state height. Okay? And it said that class D at 3 kilometers. Okay, class D, 3 kilometers. So let's come to here. Student, class D, more than 1, right? So this 2 value, this 3 value. Understand? Class D, right? Class D and 3 kilometers, so more than 3. So you need to use this 3. So we can find out SY and SZ. Understand? 听懂吗? Understand? Okay, and finally we can use this formula. Okay, we can use this formula. Okay, we just plug in all the parameters. 这个教科书有. Actually, this one is in textbook. Okay, we can find a solution in textbook. Okay, if you want to take a photo, just take a photo. But you can find this in the textbook. Let me enlarge this. Okay, so let me finish this then before we end today. Delta H, use this formula, right? 9-27. Okay? And the question already give you, this is D class. So this is D class, which means this is neutral. And also give you the distance over 1. is 3 over 1. So you need to use CDF parameter. Okay? So use this formula. 9-28 and 9-29. 9-28 and 9-29. Okay, and this is from the table. Table 9-14. OK， 听懂吗？因为它是 D 嘛，因为它是 D， 它是 D， 它是猪，对不对？那个 parameter 用，然后大于3，所以是 CDF。Then you can find out X, Y, and Z. So after that, you got everything. Then you use 9-25. Use 9-25. Okay, use 9-25. To find out the Gaussian's equation for ground level concentrations of the pollutant perfume. Okay, pollutant, not the food. Okay, let's take a short break.